So this is going to be the last section that we're going to do from chapter 10, and then we're going to jump into only selected sections from chapter 12, but that's all on circles as well. Today's lesson is going to be on areas of sectors and segments. I know that we're going out a little order here. Obviously, you guys know how to find the area of a circle because we just did the chapter on surface area of things like cylinders, and you need to know the formula for the area of a circle to be able to do that. So what is the formula for the area of a circle? Area equals pi r squared. So the area of a circle is equal to pi times the radius squared. I know we've discussed this a little bit, how you come up with this formula. At the time that we developed this formula, we had known how to find the area of a rectangle, a square, and a triangle, but that was pretty much it. Maybe a parallelogram as well. And we were trying to figure out how to make a circle into one of these figures. We talked about the fact that you could slice it, and if we sliced it only into 4 sections and arranged them in a clever way, you would have something like this. Now, this does not look like a rectangle, a square, a triangle, or a parallelogram, but it looks closer to one of those than it was before. So this would be if you have 4 slices. Then what we did was we sliced it into 8 slices, and we looked at what that looked like to try to figure out if it became more like a rectangle or less like a rectangle. So people at home, you're not going to be able to experience this because I actually did this process with some circles. People in class, take a peek over here. So this is what it looks like if you slice it into, this is actually a circle, I sliced it into 4 slices. Does that look like a rectangle? A little bit, not really, because it has the Humpty Hump on top and it has the Humpty Hump on bottom, and the side over here is definitely not vertical. So what I did was I took that same exact circle and I divided it into 8 segments, and this is what it looked like. Does it look more or less like a rectangle than the other one? More. Why? Because the top is less Humpty Hump, and so is the bottom, and the side is more vertical. So I said, let's go ahead and push it to 16. So here is 16 slices set next to one another. Notice the top and bottom are even less Humpty Hump. It's almost flat, and the side is almost vertical. So then I push to 32, and this is what 32 looks like. What do you notice about the top and bottom? They look pretty much flat. What do you notice about the side? It looks almost vertical. Now the thing here is this is only 32. In the grand scheme of things, when you're talking math, 32 is a very, very small number. If I push to 64, this thing would look like a rectangle. We only went from 0. We can go all the way as close to infinity as we want. We only went to 32 here, and it's almost a rectangle. So this is kind of like a calculus-based lesson. You could go over and make it 64, and what calc is going to do is calc is going to push it towards infinity. And then a kid in class says, hey, infinity is not a real number. How do you get to infinity? How am I going to slice infinitely many? And I say, okay, well, slice as close to infinity as you want. 32 is almost good enough. It's almost flat on top and bottom. 64 would be very close. If you went to 1,000, which is still a very, very small number in math, that is going to be almost perfect. Like the error, the fact that it's not perfectly flat on top would almost be negligible. Like it's barely not even there, and the side would almost be vertical. So this is what 32 looks like. So let's go ahead back to developing the formula. So people at home, I just showed them what it looked like if you had 8 slices and 16 slices, and then I went to 32, and it was almost a rectangle. Let's say we push to 100 slices. What that's going to look like is almost like a rectangle. It's going to look like this, and those are all the triangles, and the top is almost flat and the bottom is almost flat. So my question for you guys is, how much of the circumference is going to be down below? Looking at this right here. Anybody? Half. And if 2 pi r is circumference, then what is it down below? What is half of 2 pi r? Pi r. Ta-da! So the bottom is pi r. Now we just need to know what this side is, because a rectangle is base times height. What is that going to be? What is it? R. And when you find the area of this thing, pi r, the base, times another r, what does that give you? Pi r squared. Now, this is just one way you can have an calculus-based approach. The other way they would do it in calculus is they would say, hey, instead of this, let's think if you had a rectangle and you stacked one that was a little smaller on top, a little smaller, and then you did the same thing down here. Does that look like a circle? Kind of, but it's all jiggity-jaggedy. How do we make it less jiggity-jaggedy? This is only like 6 rectangles. What can we do to make it less steppy? Make it 1,000, make it 1,000,000, and we can go over and push this as close to infinity as we want, to the point where the little jiggity-jaggedy, I mean everything that we look at, hey, does that look like it's a perfect curve? It sure does. Now, if anybody got out of their desk and went and looked at this is pixels. The pixels are actually little boxes. This thing is not perfectly curved. Our brain is just thinking it's curved because it's not close enough and doesn't see the pixels. All right, so I know you guys are all familiar with the formula, so I'm not gonna like bore you with a basic problem. Let's go ahead and do one difficult problem together, and then difficult because of radicals, and then I'm gonna have you guys try 2 on your own. So on this one right here, we know it's pi r squared, so we need to know r. The beauty of this formula is there's only one variable. Other formulas, you had like slant height and vertical height and side length and this, that, and the other. This is one piece that you need. So how do we get from here to here on a 30, 60, 90? Divide by rad 3. Fantastic. Divide by rad 3. And that's going to give you 10 rad 3 over 3. And we could just put that into our formula. Pi times 10 rad 3 over 3 squared. Now, something that's super important and probably one of the biggest mistakes that people make is this. If you had like x plus 3 squared, people always try to distribute in every math class, algebra 1, algebra 2, pre-calc, calculus. Your brain always wants to do that. You're not allowed to do that. You can't distribute an exponent. But if you have everything inside the parentheses that's connected by multiplication or division, you can apply the exponent. So what we can do here is say 10 squared. What is 10 squared? 100. What is rad 3 times rad 3? 3. What is 3 times 3? You get 300 over 9 pi. And someone is going to math frac that baby, or do it in your head by dividing by 3. 100 over 3. Okay. So it's going to be 100 over 3 pi. And that would be inches squared. Questions? I might actually crank through these problems with you, and then that way you can do your practice on the homework, and we'll hopefully have some time in class. Next one, we know it's pi r squared. So how do I get from here to here on a 45, 45, 90 triangle? Multiply, because it's getting bigger, by rad 2. So we know this thing is 8 rad 2. So what is the radius going to be? 4 rad 2. So it's pi 4 rad 2 squared. Is there addition or subtraction inside of your parentheses? Nope. So we can go over and apply this in. 4 squared is 16. Rad 2 times rad 2 is 2, or rad 4, which is 2. And that gives you 32 pi centimeters squared. Anybody have any questions on that? I know that you guys have graduated from me just going, what is the area? This is 5. So we're just doing practice problems that'll help you with algebra 2. Yeah, what's up? You good? Cool. All right, the next problem. We know that it's pi r squared. We don't have the radius though. Any ideas on how we're going to find that radius? Pythagorean theorem. You have 2 sides of a triangle. Find the third side using Pythagorean theorem. So this is basically what it looks like. This is a 6 down here. This is a 10. And before we bust out a squared, b squared, and c squared, we always check 3, 4, 5, 5, 12, 13, 7, 24, 25. It's 8 because it's a 3, 4, 5 times 2. So they say that inside, we're going to talk about this in the next chapter, what that's called, but that's 8 and that's 2. Everybody good with the whole side being 8? What's the radius going to be then? 4. So we can say pi times 4 squared. And that gives us 16 pi inches squared. I got one more, and this one is going to take some skills with your calculator. Pi r squared, we don't have the r. How could I go about solving for this? Can I do trig? What's the rule with trig? You can only do trig if you have right triangle. Do we have a right triangle? No. But what we have been given is that the area is 100. Do you remember, when all else fails, draw a picture or write down the formula? Is there any formula that we would usually do to find the area of this figure? We can't 1/2 base times height. We don't have a height here, though. There's a different formula for finding the area of a triangle. Do you guys remember that? Like it was a specialty tool formula? Fantastic. It is 1/2. Oh, not AP. Oops. Someone else? Yeah? There we go. Okay, you guys should remember this. The area equals 1/2 side sine of the angle. So I could say 100 equals 1/2 side, which is 20, times side, which is x, times the sine of the angle between them. Now that's ugly. I need to get rid of 1/2, I need to get rid of 20, and I need to get rid of sine of a. Does anybody have any ideas of how we could do that? What is the first thing we want to get rid of? Sure, let's get rid of 1/2. How do I do that? Multiply both sides by 2. So that's going to be 200 equals 20x sine of a. At this point, what could I do? Why isn't it sine of 40? Oh, good point. Sine of 40. Thank you. We can actually put a 40 in because we know that. Okay, at this point, what can we do? Let's divide by 20. 200 divided by 20 is 10. 10 equals x times sine of 40. How do I get that x by itself? Divide by sine of 40. So we have pi times 10 over sine of 40 squared. Now here's where it gets a little tricky, trying to get that into your calculator. There's many different ways you can do this. Personally, me, since I have a graphing calculator, I usually put that in my calculator and then I would store it as x. Then I'd be able to say x squared times pi. But you could also say, in parentheses, 10 divided by sine of 40, parentheses, times 10 divided by sine of 40. So I'm going to put that in my calculator. Making sure that my calculator is in degree mode. Mode, degree, I am in degree mode, cool. So 10 divided by sine of 40 gives me 15.557, blah, 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 blah. I don't care. Sine, I'm going to store that as x. Now I'm going to say x squared times pi. You see, if you have a graphing calculator, look at the left-hand side down towards the bottom, right above on. It says store. Press that button, and then press the button 1 over and 1 down from second, the xt, blah, 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 blah. Press enter. Now your calculator, until you change that, thinks that x means that exact number. If you put this in your calculator right, you should have gotten 760.4. Not times 2, square it. Square it and then say times pi. Yes? Does it stay as x forever? Forever until you change it, unless you're graphing. If you graph, it still thinks x means variable. Okay, that was a bunch of stuff of just practice. It wasn't the meat of the lesson. Does anybody have any questions on that? Now let's move to the meat of the lesson. The shape that you see here is called a sector. If I was blindfolded, what would you tell me that a sector is? Part of what of the circle, though? Part of area. Now, we already did part of circumference. We already knew that part was the arc over 360. That means part. What was of from algebra 1? And what is area now? Let's change our formula a bit. What should I put in here instead of 2 pi r? We're not doing part of circumference. Pi r squared. Rather than putting these words, I'm just going to put measure of AB over 360. That's part of area. Does anybody have any questions on that? Let's go ahead and do one then. So on this one right here, it's the 72 out of 360. That tells me what part of the circle it is. Part of area. Part of area. So that could be thought of as this arc or this central angle. They mean the same exact thing. Or they equal the same thing. What do you guys get when you math frac 72 over 360 times 225 math frac? 45 pi. Great. Anybody have any questions on that? Let's go ahead and do the next one. All right, on this one right here, someone, can someone help me? What am I going to write down here? 260 over 360, because that's what's left over here, times pi times r squared, which is 64. What's it give me? So anybody go ahead and put 260 over 360 or 26 over 36 times 64 math frac. 416 over 9, fantastic. 416 over 9 pi meters squared. Anybody have any questions on that? No? Okay, on the next one, we know it's supposed to be whatever this angle is, or the arc over 360 times pi r squared. So we're going to have AB over 360 times pi 4 squared. Now here's the issue. We do not know what that angle is. We do know that if that's 4, then this is 4. What I want you to do, people at home, I want you to pause the video and try to figure out how you could figure out what this angle is right here. People in class, check in with your neighbors and figure out how you can come up with that angle. Does anybody have any ideas about how we can find out what that angle is? Yes. You could do inverse trig, because this is a right triangle. So you could say opposite and hypotenuse is sine. Sine of x equals opposite over hypotenuse. And you could do inverse sine. You would get, did someone do it a different way and get an answer? Or see a pattern that may have told you what the angle is? I think I heard. It's a 30, 60, 90. Because if it's a right triangle and the short side doubles to get to the long side, that has to be a 30, 60, 90. Now, if you did this method, you would also get 30 degrees. Great job to both of you guys. One was a method, one was just being able to see it. Now, that only works. Your little method of the, oh, this is half of whatever this is, only works if it's a right triangle, though. So we have 30 over 360 times pi times 16. And when you math frac that, baby, what do you get? What do you get? 4 over 3. Okay, so we're going to get 4 over 3 pi inches squared. I don't know if that's the units, but that's what I'm running with. So all of those, we're talking about the whole entire piece of pizza, which is called a sector. Now what we're going to do is talk about, I know it's a sector again, that's because I copied and pasted when I was making this. It's supposed to be segment. The segment is just going to be the sector minus the triangle. So if you ever do the whole entire thing, take away the triangle, it's kind of what you would think of as the crust, even though the crust is uniform, and this is obviously not, but it's closest to being like a crust. So this would be considered one of the easier problems to do because it's a right triangle. So you're going to have the whole entire thing. You're then going to take away the triangle, and then you're going to have your answer. Every single year, people forget to subtract the triangle. So on this, we know it's going to be 90 degrees over the 360 times pi times 10 squared minus, we're lucky because it is a 1/2 10 by 10. This is the right triangle. Those are the easy ones.
How do you get the 1/2?
1/2 base times height because it's a triangle. So that reduces to 1/4 of 100 minus 50. And that gives us 25 pi minus 50. Are we able to combine those things? Are they like terms? Nope. Does anybody have any questions on the easy problem when you have a right triangle in here? Questions on that? Let's go ahead, and if you don't have any questions on the right triangle one, we can skip practice A and let's just do practice B. This is obviously going to be the whole entire thing minus the triangle gives us our answer. Now on your homework, it says give it to as a radical. The easiest way to do these is 1/2 side 1, side 2, sine of the angle between the sides. That's the easiest way to find the area of a triangle. But in this case, because it would be 1/2 18 times 18 times sine of 60, but that's going to give you a decimal. And on the homework, it asks for a radical, which tells you 30, 60, 90s. So this is going to be 60 over 360 times pi r squared minus, technically we could do 1/2 base times height. We could do 1/2 side 1, side 2, sine of the angle, but I'm telling you not to do that because I don't want a decimal. Or you could do 1/2 apothem times perimeter because it is a regular triangle. It is equilateral. I think I'm going to do this one. We've always gone over and said, oh, look, here's a 30, 60, 90 embedded in here. And then finally, first period, I had a kiddo say, hey, can't we, if this is 60 and that's 60, if we drop down this, isn't it another 30, 60, 90? And I said, oh, yeah, 12 years into teaching this, and finally I see that, yes. So the whole side is 18. That side must be what? 9, and then the height would be 9 rad 3. So we could do 1/2 base, 18, height, 9 rad 3. You would have gotten the same answer if you did 1/2 apothem times perimeter working on it like that. You guys do this part for me, and I'll do this. Because half of 18 is 9, and 9 times 9 rad 3 is 81 rad 3. What do you guys get when you math frac this one? 54? 54 pi. Yep. And can I combine those things? Nope. So that would be inches squared. Real quick question. If this was not 60, but that was like 73 degrees, which formula would be best? Formula A, Formula B, or Formula C? If that was 73 degrees instead of 60. B would be best, though you would get an answer as a decimal. All right, main things are making sure you guys know the difference between a sector, which is part of the area, and the segment, which is part of the area minus the triangle. People at home, thanks for watching.